Friends, let us come to the fourth chapter of our course in discrete mathematics. We introduce the relations and functions in this session. The pigeonhole principle, which is useful in theoretical computer science, also is introduced. Relations and functions. Introduction. The term relations is not confined only to mathematics. It is used almost in the same sense everywhere. We often talk about relations of the sort is a friend of, is a proof of, is a spare part of, etc. Always, these relations are described from one set of objects into another. To start with, we need the Cartesian products of sets. For two non-empty sets A and B, the Cartesian product denoted by A cross B is defined as A cross B equals set of all ordered pair AB such that A belongs to A and B belongs to B. It is a set of all ordered pairs of the type ordered pair AB in which the first coordinate A is from the first set A and the second coordinate B is from the second set B. If either of these sets is empty, then the Cartesian product also is empty. Relations are defined as subsets of Cartesian products. If R subset of A cross B, then R is called a binary relation from A into B. We denote this by R from A to B, which is read as R is a relation from A into B. Note, the sets A and B are called respectively the domain and codomain of the relation R. If there is an ordered pair AB belongs to R, then we denote it as ARB and read it as A is related to B under the relation R. Relations for which the domain and codomain coincide have special importance. If R is a relation from A into A, then R is said to be a binary relation on the set A. Most of the relations in real life situations are of this sort. As relations are basically sets, they can be defined in the roster method and in the set builder method. Suppose A and B are sets having m and n elements respectively, then the total number of relations from A into B is 2 raised to m into n. For three sets, we can define ternary relations, which is a set of ordered triples. Similarly, an n-ary relation is a set of n tuples. In large-scale computing, lot of data of various types will be required. For example, to take the profile of one student in an institution, a well-organized search among many data tables will be required. Considering each data table as a set, the profile of the student can be seen as an appropriate n tuple whose coordinates are entries from various data tables considered. The situation will be much more complex if we look into the data corresponding to a university or the data related to a railway reservation system. We can say that two data tables are related if they share some data in common. Handling data in this way as a relation is a relational model for database. It has a significant role in the field of management. RDBMS, that is, Relational Database Management System, has become an important branch in management practices. As an example, consider A to be a set of 4 computers C1, C2, C3, C4 and B a set of 3 students S1, S2, S3 who may use the computers. If no student is permitted to use any of these computers, then we get the empty set as a subset of A cross B, which makes the empty relation. It is clear that the singleton set ordered pair C1 S1 is a relation from A into B. If there is no restriction for the students to use the computers, then correspondingly we get the whole of A cross B, which is the universal relation. The set of all ordered pairs C1 S2, C1 S3, C2 S1, C2 S2, C2 S3, C3 S1, C3 S2, C3 S3, C4 S1, C4 S2, C4 S3 is another relation. Any subcollection of A cross B form a relation from the set of the 4 computers into the set of students. It is possible to describe relations between sets by simple tables. Such tables are called relation tables. Consider the following example. Let C equals set of all elements C1, C2, C3, C4 and S equals set of all elements S1, S2, S3, B2 sets. Consider the following table. Here C1, C2, C3, C4 are arranged row wise, S1, S2, S3 are arranged column wise. We can see that there are check marks in the cells corresponding to C1, S2, C2, S1, C2, S3, C3, S2, C3, S3, C4, S1, C4, S2. It is clear that there is a relation defined from C into S. It is represented by the set of all ordered pairs C1, S2, C2, S1, C2, S3, C3, S2, C3, S3, C4, S1, C4, S2. We concentrate our discussion to relations on a set. It is clear that the corresponding relation table is square shaped. Different types of binary relations on a set. First, reflexive relation. A relation on a non-empty set A is reflexive if A related to A for every A belongs to A. The corresponding table will have check mark along the main diagonal. Next, symmetric relation. A relation on a non-empty set A is symmetric if A related to B implies B related to A where AB belongs to A. The corresponding table will be symmetric about the main diagonal. Next, antisymmetric relation. A relation on a non-empty set A is antisymmetric if A related to B and B related to A implies A equals B where AB belongs to A. Next, transitive relation. A relation on a non-empty set A is transitive if A related to B and B related to C implies A related to C whenever A, B, C belongs to A. Equivalence relation. A relation on a non-empty set A is an equivalence relation if it is reflexive, symmetric and transitive. The relation table of an equivalence relation has some speciality. The table as a whole will be square shaped. Moreover, it will be a join of many square blocks such that each of the cells of the different square blocks contain check mark. It is shown in an example which will be discussed later. Next, partial order relation. A relation on a non-empty set A is a partial order relation if it is reflexive, antisymmetric and transitive. Example, consider the set of all natural numbers. A relation R is defined as A related to B if A less than or equal to B. Then R is reflexive, antisymmetric and transitive. In other words, R is a partial order relation. Next example, consider the set of all integers. A relation R is defined as A related to B if A minus B is an even number. Then R is reflexive, symmetric and transitive. In other words, R is an equivalence relation. If A minus B is the multiple of some fixed natural number, then also R is an equivalence relation. Next, consider the set of positive integers. A relation R is defined as A related to B if A is a divisor of B. Then R is a partial order relation. Next, consider the set of real numbers. A relation R is defined as A related to B if A into B greater than 0. Then R is symmetric and transitive. It fails to be reflexive since 0 related to 0 is not true. Next, consider the set of real numbers. A relation R is defined as A related to B if 1 plus A into B greater than 0. Then R is reflexive and symmetric. It fails to be transitive since the ordered pairs 2, 0 and 0 minus 2 together do not assure the existence of the ordered pair 2 minus 2. Note, an important property of an equivalence relation is that it makes a partition of the set. By a partition, we mean a collection of pairwise disjoint subsets whose union is the set. If a relation R is defined on the set of integers as A related to B if A minus B is a multiple of 3, then the set of integers is partitioned into the 3 sets Z0 equals set of all elements 0, 3, 6, etc. minus 3, minus 6, etc. Z1 equals set of all elements 1, 4, 7, etc. minus 2, minus 5, etc. and Z2 equals set of all elements 2, 5, 8, etc. minus 1, minus 4, etc. Clearly, the 3 sets are pairwise disjoint and their union is the set of all integers. It is possible to make out the equivalence relation when a non-empty set and a partition of it are given. For instance, consider the following example. Let A equals set of all elements A, B, C, D, E, F be a set for which the partition is defined by the sets singleton set A, set of all elements B, C, D and set of all elements E, F. It is simple to verify that R equals set of all ordered pairs AA, BB, BC, BD, CB, CC, CD, DB, DC, DD, EE, EF, FE, FF is an equivalence relation on A producing the given partition. The method is to write the universal relation on each subset of the partition and then take their union. Partially ordered set. A non-empty set together with a partial order relation is called a partially ordered set. Usually, a partial order is denoted by less than or equal to. An element A is said to cover an element B under a partial order relation less than or equal to on a set if B less than or equal to A. If A covers all other elements of the chain containing it, then it is called a maximal element of the set. Note, it is possible to define lower bound and upper bound for elements in a partially ordered set. Let A and B be two elements of a partial order set A less than or equal to. If C belongs to A is such that C less than or equal to A and C less than or equal to B, then C is called a lower bound of A and B. If C is a lower bound of A and B and for any lower bound D of A and B we have D less than or equal to C, then C is called the greatest lower bound. If C belongs to A is such that A less than or equal to C and B less than or equal to C, then C is called an upper bound of A and B. A least upper bound can be defined in a similar way. If U is an upper bound of A and B and for any upper bound D of A and B we have U less than or equal to D, then U is called the least upper bound. Next, chain or totally ordered set. A chain or a totally ordered set is a partially ordered set in which any two elements are related. The corresponding equivalence is called a total order relation. The number of elements in a chain is called its length. Next, anti-chain. A subset of a partially ordered set is called an anti-chain if no two distinct elements of the subset are related. Example, let A equals set of all elements 1, 2, 3, 5, 7, 22, 39, 85, 88, 133. Let R be a binary relation defined on A such that ordered pair AI AJ belongs to R if and only if AI is a factor of AG. Then R is a partial order on A and the different chains are set of all elements 1, 2, 22, 88, set of all elements 1, 3, 39, set of all elements 1, 5, 85 and set of all elements 1, 7, 133. Here the sets set of all elements 2, 3, 5, 7, set of all elements 2, 3, 85, 133, set of all elements 3, 5, 7, 22, are some of the anti-chains. Next example, let A equals set of all elements A1, A2, A3, etc. An be the set of all courses required for graduation. Let R be a reflexive binary relation defined on A such that for Ai not equal to Aj, ordered pair Ai Aj belongs to R if and only if course Ai is a prerequisite of course Aj. Then R is antisymmetric and transitive. So, R is a partial order relation. Suppose that C is the length of the longest chain in the partially ordered set A. This means that there are C courses that must be taken one after another. Thus, under no circumstances will be a student able to finish the required courses in less than C semesters. Suppose that D is the size of the largest anti-chain in the partially ordered set A. It means that a student will be able to take at most D required courses in any semester. The following theorem shows the relationship between chains and anti-chains. The theorem states that let P less than or equal to be a partially ordered set. Suppose the length of the longest chain in P is n. Then the elements in P can be partitioned into n disjoint anti-chains. The proof is by induction on n. When n equals 1, there is nothing to prove. As the induction step, let us assume the theorem to be true when n minus 1 is the length of the longest chain in a partially ordered set. Now, let P be a partially ordered set in which the length of the longest chain is n. Let M denote the set of maximal elements in P. Then, M is a non-empty anti-chain in P. Consider the partially ordered set P difference M less than or equal to. There is no chain of length n in P difference M. The length of the longest chain will be at most n minus 1. If the length of the longest chain is less than n minus 1, then M must contain 2 or more elements that are members of the same chain, which cannot be possible. So, the length of the longest chain is equal to n minus 1. By the induction hypothesis, P difference M can be partitioned into n minus 1 disjoint anti-chains. Thus, P can be partitioned into n disjoint anti-chains. Corollary, let P less than or equal to be a partially ordered set consisting of mn plus 1 elements. Either there is an anti-chain consisting of m plus 1 elements or there is a chain of length n plus 1 in P. Functions and pigeonhole principle. Consider A to be a set of school children and B to be a set of women. Consider two relations R and S from A to B be given as sets of ordered pairs of the form ordered pair AB where A belongs to A and B belongs to B. Let ARB stands for B is a teacher of A and ASB stands for B is the mother of A. There is a striking difference between these two relations. In the relation R, it is possible that certain members of A to have more than one corresponding member in the set B, whereas in the relation S, corresponding to any member of A, there cannot be more than one member in the set B. When stated formally, there are relations in which the conditions A related to B and A related to C together will imply B equals C. Symbolically, ordered pair AB and ordered pair AC are in the relation will imply B equals C. Such a relation is called a function. When A and B are two non-empty sets, then the number of functions will be much less than the number of relations. If A has m elements and B has n elements, then the number of functions from A into B is n raised to m and that from B into A is m raised to n. Pigeonhole principle is a well-known technique for proving certain mathematical statements. This is also known as shoebox argument or Dirichlet-Drouin principle. The principle says that if there are many pigeons and a few pigeonholes, then there must be some pigeonhole occupied by more than one pigeons. The formal statement can be seen as follows. Let D and R be finite sets with number of elements of D greater than number of elements of R. Then, for any function f from D to R, there exists D1, D2 belongs to D with D1 not equal to D2 such that f of D1 equals f of D2. The pigeonhole principle is applied in the following examples. First example, a girl wants to prepare for a chess championship match by playing some practice games in 77 days. Suppose that she plays at least one game a day but no more than 132 games altogether. Then it can be shown that in any schedule of the games there is a period of consecutive days within which she plays exactly 21 games. Let AI denote the total number of games she plays up to the ith day. Then the sequence A1, A2, etc. A77 is monotonically increasing with A1 greater than or equal to 1 and A77 less than or equal to 132. The sequence A1 plus 21, A2 plus 21, etc. A77 plus 21 also is monotonically increasing with A77 plus 21 less than or equal to 153. Since the values of the 154 numbers A1, A2, etc. A77, A1 plus 21, A2 plus 21, etc. A77 plus 21 range from 1 to 153, two of them must be the same. Moreover, since both the sequences A1, A2, etc. A77 and A1 plus 21, A2 plus 21, etc. A77 plus 21 are monotonically increasing, there must be ij such that AI equals aj plus 21. Next example, in any group of 6 persons, either there are 3 persons who are mutual friends or there are 3 persons who are complete strangers to each other. Let A be one member of the group. According to pigeonhole principle, either there are 3 or more persons who are friends of A or there are 3 or more persons who are strangers to A. Let us consider the former case only, since the latter case can be resolved by a similar argument. Let B, C, D denote the friends of A. If any two of B, C, D know each other, then these two together with A form a friendly threesome. On the other hand, if no two of B, C, D know each other, then they are 3 persons who are strangers to each other. Let us summarize the main points we have discussed in this session. The concepts of relations and functions were introduced. Different types of binary relations were defined and illustrated with examples. The pigeonhole principle, a useful tool for solving many problems in real-life situations, was presented. The following questions are given to you to practice. First, draw the relation table for the relation R from A to B given by R equals set of all ordered pairs A1, B2, C1, A3, D4, C5, C6, where A and B are suitable sets. Obtain the partition of set of all x such that 1 less than or equal to x less than or equal to 9 and x is an integer under the equivalence relation x related to y if and only if x is congruent to y mod 6. On the set of all elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 15, 16, define a relation by the set of all ordered pairs xy such that x is a divisor of y. Is it a partial order relation? If yes, then obtain all the chains. Next, consider the relation set of all ordered pairs xy such that x square plus y square equals 1 on the set of real numbers. Is it a function? Give reason. Next, show that among n plus 1 arbitrarily chosen integers, there are 2 whose difference is divisible by n. The following books are suggested for further reading. Elements of Discrete Mathematics by C. L. Liu, Tata McGraw-Hill Publishing Company, 2nd edition. Discrete Mathematics and its Application, 6th edition by Kenneth Rosen, TMH Education Private Limited. Set Theory and Related Topics by Seymour Lipschitz, Shorm's Outline Series, 2nd edition, TMH Education Private Limited. Hope you have followed this session. We will continue our discussion with graphs and planar graphs in the next session. Till then, goodbye.